our first example of a problem that falls into the category of related rates. So what I've got here is a scenario where I've got a wall over here on the left side and then the ground here across the bottom. And there's this ladder that is leaning up against the wall. So there's this ladder leading up against the wall. The ladder is a 10-foot ladder. And so here I am, standing at the top of the ladder. Hanging out at the top of the ladder, washing my window, and along comes this little guy down here. He's got a little tail on the end here, and he's got some ears on his head.
He's a monkey from Who's Your Boss.
All right, this little gremlin that has come across the ground here comes over to this ladder, grabs the bottom of the ladder, and starts pulling the ladder away from the wall. Okay? So I'm standing on the top of this ladder trying to wash my window, and here this little gremlin comes. He takes the bottom of the ladder and starts pulling it away from the wall. So my first reaction is, ah, what am I supposed to do now? And I throw my bucket of water in the air. Okay? And as I throw the bucket of water in the air, and this gremlin is pulling the bottom of the ladder away from the wall, what's happening to me besides the fact that I'm panicking?
You're going down in height.
What's that?
You're going down in height.
Yeah, I'm dropping down in height. So as the bottom of the ladder is moving out, the top of the ladder is moving down. And so here I am yelling and putting my arms up in the air and saying, help me, I'm falling. This ladder is sliding down the wall. Okay? Now, right at this point, this is a perfect opportunity to think about calculus. So I'm falling down the wall, and I say, okay, this is a great idea. I'm going to teach my calculus class a little bit about some related rates. So this little gremlin guy down here, okay, he is pulling the ladder out from the bottom of the wall at a rate of 1 foot per second. And so as this gremlin is pulling the ladder away at a rate of 1 foot per second, the question is, how fast am I falling down the wall? So the bottom, we'll write this out, the bottom of the ladder is being pulled away at a rate of 1 foot per second. Now, the first thing that we might want to think about here is, if the bottom of this ladder is being pulled away from the wall at a rate of 1 foot per second, am I falling at a constant rate? The bottom's being pulled out at a constant rate. Am I also falling at a constant rate?
Unless you decide to hold on.
Well, assuming I'm not holding on, and that this ladder is, and that this ladder is just sliding down, consistent with this being pulled out at 1 foot per second, are we falling at a constant rate?
Yeah.
Yes, maybe. Okay.
Well, except that
Would your
if
weight
that's
be
ever
a
happened to you, you don't fall at a constant rate.
You'll wait quicker.
How does it happen? Does this happen to you, Jeff?
Not really. I mean, not like that. But I just know that as it gets closer to the bottom, there are other factors that play into that, like the
Gravity?
pressure on the
Like
wall,
the weight, your weight.
your weight, you know.
So the weight here is, I mean, in terms of, this is not a free-falling body because
Would you?
we're being held, we're being restricted by this bottom of the ladder here is literally moving at 1 foot per second away. So gravity over here is not necessarily going to be playing a role.
Well, except that at the top, you're pushing against the wall
Okay.
with more force than you are at the bottom. So that, I would think that physics would say that it wouldn't be constant, even though this may work out to be constant.
Well,
Could you?
let's find out.
Well, they would try it out in an experiment.
Yeah.
All right. Did any of you bring a ladder with you today?
I
I
fell.
carry one in
just
my
fell. I
backpack
held
at all
on.
times.
What's that?
So, for example, if your height is 12 foot off the wall,
Like all that, just stack
so your
together,
height is
and
going to
you
be
just pull it
1
apart.
foot per second on the y-axis as well.
Like fits into something like this.
So you're saying that if this bottom is being moved out at 1 foot per second, then you're suggesting that this y value should also be changing exactly 1 foot per second as well. Huh?
So it looks like the,
Pretending to get drunk in
it looks like
class.
a trig function. It's the
Is this a
relationship
7-Eleven purchase?
between the height of the side opposite that angle where the gremlin is and the length
Yeah, I'll do
along
one.
the
It's so easy.
base along the
Stay
ground.
distinct.
So my expectation is it's going to be not constant acceleration.
Okay, so, all right, so some of you are believing that this speed is going to be a constant speed, and some of you are believing, no, this is not going to be a constant speed, that as the ladder gets closer to the ground, that maybe the speed is going to speed up down here. Okay. So let's see what happens. All right, so the overall question that we're going to ask is, how fast is the top of the ladder moving down the wall when the bottom is 6 feet from the wall. Okay. So this will be our overarching question. Once the gremlin has pulled the bottom of the ladder away by exactly 6 feet, at that moment in time, how fast is the top of the ladder moving down the wall? In order to answer that question, I think we're going to be able to see whether or not our speed is constant or not.
Is it 6 feet from the wall or 6 feet after he's moved it 6 feet?
Oh, 6 feet from the wall, so that we're trying to find the moment in time when this distance is exactly 6 feet. Okay. So this is our question.
6 feet from the.
Now, in order
6
to
feet.
answer this question, I like Tom's observation about noticing that what we have here is really a right triangle. Okay, and so this may involve some trig functions, but maybe we don't have to go quite as far as trig functions. The second that I see right triangles, what's the very first theorem you think of? Yeah, Pythagorean theorem. And the Pythagorean theorem says that if I label my two sides, let's label this bottom side as x, and the vertical distance here as y. And our hypotenuse in this case is always going to be 10. Our ladder is not an extension ladder, it's a 10-foot ladder. Okay. And so, in that case, we can write down the Pythagorean theorem, which says that x squared plus y squared is equal to 10 squared. Now, when I think about this situation here, I want to think about this. Oh, thank you. Thanks for trying. So when I think about this situation, I want to think about this as a movie. Okay? And so I want to imagine that I have this whole scenario playing out. The ladder's being pulled out across the ground. I'm falling down on this top side. And so throughout the movie, the x value and the y value are changing, whereas the 10 feet is not changing. And in particular, this x value and this y value are changing with time. So over time, the x value and the y value are changing. And so another way that I might think about this function, or this equation that I have written up here, is that x and y both depend on time. So I might write this equation up here, this relationship relating my sides of my triangle, as x is a function of time. And so I might write this as x of t squared. And y is also a function of time. So rather than writing y, I might think of y as a function of time. And then my 10 squared is 100 on the right side. Okay. Now, the main question that we're asking here is how fast is the top of the ladder moving down the wall? Well, how fast is the ladder moving down the wall? That's asking us how fast is y changing. And so our motion is described by dy over dt. How is y changing with respect to time? And the motion in the x direction, well, how is this x distance changing? Well, that's described by dx over dt. How is x changing with respect to time? Now, our goal here is to find how fast the top of the ladder is moving down the wall. And so our goal is to find dy over dt when the bottom of the ladder is 6 feet, meaning when x is equal to 6 feet. So what we've done now is we've changed this movie scenario where we've got our ladder moving, the bottom is moving out, x and y are both changing as we play our movie, and so they're changing with respect to time. And we've written down a relationship. Now within this relationship over here, I'd like to find eventually dy over dt. And I don't have that here, but I do see a y in here. So if I take a derivative of this expression with respect to time, I'm going to get myself a dy over dt. So when I do this, I'm now going to take my derivative with respect to time. So the first function that I have here is x of t, and that's squared. Okay? And I've got something fancy inside the parentheses, so I'm going to have to use my chain rule. And my chain rule says, okay, take the derivative of the outside, keeping the inside the same. So I have to bring the 2 down, keeping the inside the same, now raised to the first power, times the derivative of the inside, x prime of t. So remember, all of this is happening in the motion. Okay, so everything's changing here, and we're taking our derivatives while we still have all of our changing variables going on. Our second term here, y of t squared, when I take the derivative of that with respect to time, y of t is fancier, y is a function of t, and so I take my derivative of my outside, keeping the inside the same, so 2 times y of t, times the derivative of the inside, y prime of t. And now on the right side, when I take the derivative of 100, I get 0. Okay, so what we've just done is we've just done implicit differentiation on this equation right here. And what we're thinking of is our initial relationship, x squared plus y squared equals 100. I'm thinking of both this x and y as both of those are functions of time. So when I take my derivatives, I have to apply the chain rule. And so the chain rule shows up both when I take the derivative of x and when I take the derivative of y, because I'm thinking of both of those as functions of time. Okay, so I'm going to rewrite this now. Rather than using this longer notation, x is a function of time, I'm just going to write it as x. So I've got 2x times dx over dt, that's my x prime, plus 2y times dy over dt is equal to 0. All right, now our goal is to find dy over dt. So let's go ahead and solve this equation up here for dy over dt. In order to do that, I've got to move this 2x times dx dt over to the right side. So I have 2y times dy over dt is equal to negative 2x times dx over dt. And then I'll need to divide both sides by 2y. So we have dy over dt is equal to, well, my 't's cancel, and I'm left with negative x times dx over dt divided by y. Okay, so let's stop here for just a second. Let's think about what we've done. We're trying to answer the question of how fast is y changing? In other words, how fast is the top of the ladder falling down the wall? And what we have over here is an expression for how fast that y value is changing. So y is changing with respect to time, and that change is being described by this formula on the right side. Now, the dx dt, that we know is going to be 1, so we're having a constant change in the x value. But once we plug that 1 in here, will our speed, will dy over dt, always be the same no matter what x and y are equal to? No, why do you say no?
Because your dy is what's changing, and your division is by something that's going to be changing for each time you take that value.
Okay, yeah, we've got this fraction over here, and even if I plug in dx over dt to be 1, I still have 2 other values that are changing. And so if I plug in maybe a very small x and a very large y, that dy over dt is going to be different than if I plug in a different x value. And so this is actually going to change. Our y value is, our speed in the y direction is not going to be the same at all times. All right, so this is our speed. In other words, how y is changing at any moment in time. So how fast y changes at any moment in time. Now, for our specific example, we want to know how fast is the top of the ladder moving down the wall when the bottom is 6 feet from the wall. And so when the bottom is 6 feet from the wall, well, at that moment in time, we've stopped our moving. We've taken a snapshot. Our x value is going to be 6. Our dx over dt, our gremlin, is still moving our ladder at 1 foot per second. And so now we can plug in x and we can plug in dx dt. We still need to plug in a value for y. So if we want to know what the y value should be over here, how are we going to figure that out? Yeah, Pythagorean theorem is what we need. Okay? We know our x value is 6. Our hypotenuse is 10, and so we can figure out what y is equal to. So for y, we've got x squared plus y squared equals 100. So that's 6 squared plus y squared is equal to 100. We can solve for y squared. 36 plus y squared is equal to 100. We can subtract off that 36, and we get 64. And then when we take the square root of both sides, we technically get plus or minus 8, but we're talking about a length, and so this is a positive value. So now we've got values for x, dx dt, and y. And so when I plug these in, dy over dt becomes negative 6 feet times 1 foot per second divided by 8 feet. so in the end, if I crunch out all these numbers, I end up with dy over dt is equal to -3/4, and our units, the feet cancel, and we're left with feet per second. So, our gremlin has been pulling the ladder out from the bottom. This ladder is sliding out. He's pulling it out at 1 foot per second. When the bottom of the ladder is precisely 6 feet from the wall, well, I'm up here at 8 feet above the wall, number one. And number two, I'm sliding down this wall at a rate of 0.75 feet per second. The top of the ladder is falling at a rate of 3/4 of a foot per second. Yes, Robert?
Now, because you're falling down the y-axis, does that mean that your velocity is negative?
That's a really good question. So our value over there is a -3/4. So dy dt says that y is shrinking. Okay? And so in other words, in that case, because of the way we have our picture drawn, that means falling. And so rather over here, I would say that if I'm writing this out in words, the word falling replaces my negative sign. And so falling at a rate of 3/4 of a feet per second. Or I could say that the rate of change of y is -3/4 of a foot per second. All right. So I would encourage you to try this, where instead of saying the bottom is 6 feet from the wall, say, okay, well maybe the bottom is only 3 feet from the wall. Then, that's going to change your x, it's going to change your y, and see if your rate is the same or different than this value. If you get -3/4 again, then you've at least kind of convinced yourself that the rate is constant along that y value. And if you get something different, then hopefully you've convinced yourself that the speed changes as we pull away from the wall. Okay, are there any questions about this example here? Okay, well, let's pause here